So this is Chapter 1, Digital Electronics for ELE 212. So the first thing we want to do is understand that we're going to be working with digital signals, and those are 0 to 5 volts. But in some cases, we may be working with signals that are 0 to 3 volts. In some cases, very rare, we'll be going above 5. But for example, the 555 timer, we may move that up to 9 volts to let you see that it actually can handle that voltage. But 99% of this course is going to be voltages that are about 5 volts. So first thing we have to do is we have to understand what is a digital signal. So a digital signal, if we look at what a digital signal is, a digital signal basically is a square wave that has a high peak and a low peak. So basically, and it alternates. So most of the time, our digital signals are square waves. So we can say a digital is a square wave. Has an amplitude. So we'll say this is the amplitude from here to here of 5 volts. And it has some sort of pulse width. Some sort of cycle. Has some sort of cycle, and it actually has a pulse width. Right? And if we look at the cycle itself, this is one period. And if we say that, if we know this time, we call that time. And we can say that frequency is equal to 1 over time. All right. The pulse width is important, and we'll get into that a little later on. But we can actually vary the pulse width, and this pulse width has again some time to it. A lot of times, what we're looking for is not the voltage, but can we vary the pulse width, or how many cycles we're actually going, how many cycles we're doing per second, or our frequency. Most of the frequencies we were working with are in the 1 kHz and above. We may go down to 60 hertz. Might play around, but you're going to be a little bit higher low end. So basically, a digital signal is basically a square wave that has some sort of pulse width and it has some sort of cycle. All right, so we were talking a little bit about the digital signal itself. So basically, like I said, the pulse width, and then we call this the cycle. This is actually called the period or the cycle. And we can actually get from here, we can actually get the frequency. F is the frequency, and frequency is measured in hertz. I forgot the units, hertz. So if you have any questions on that, just holler at me, drop me an email, stop by my office. So basically on this is digital signal. Now, you probably ask yourself, well, what's so great about a digital signal? Well, let's look at a digital signal first of all. Let's say we have a repeating pattern that looks like this. And then we have something that comes off, and then it goes back on, and then it comes back and does that. And let's say this bottom one, let's say this is our signal. And this is our clock. And I'll talk about clocks here in a minute. So let's say our clock is doing this, and then it's doing this, and it's doing that. I know this is really, really generic, but hopefully it gets you an idea that what is going on. So if we look at our clock signal, we look at the rising edge of these clocks right here. So this is our clock, and this is our signal. So this one will be a 1 because this is a high. Here's 5 volts. But if we look at this one, it's coming up here, but that's a 0. So if we look at this one, this is a high, so this is going to be a high right here. This one should be over here a little bit. So that should be there. Look at these two, that should be lows, because there's 0 volts. 0 volts here, there's 5 volts. And we keep going on like this. Now, if you notice that we're actually using what we call binary numbers down here. And binary numbers, we'll talk about those later, binary numbers are numbers that are in digital. These are binary numbers, and these are digital numbers. Why? Because computers only work on 1 and 0s. That'll be on a quiz. So basically, a digital signal is a repeating pattern of square waves, and we can basically get a lot of information out those square waves. So you probably ask yourself what uses this technology? Well, it's our life. To be honest with you, this is our life. Everything that we use today to extract information is in what we call binary numbers or bits or bytes, and this is information we use off of a square wave, and this is how computers are built. This is how we transmit information over the web, etc. So anything that's digital, we're transmitting over the web through a square wave. And number one, it's a lot faster than an analog signal. Well, you ask yourself, what's an analog signal? Well, an analog signal is a varying signal. So this is just varying. This is analog, and it varies. So basically, we can get this, and it could look like this. It could look like anything, but an analog signal it has some height, but it also varies in it. So this could be an analog signal, could be something that's coming from a temperature sensor, 4 to 20 milliamps. So transmitting this over the web is not really ideal. What we like to do is transmit something like this over the web, where it's basically simple, ones and zeros, and then we can decode it. So in order to generate a digital signal, we need to either have a piece of equipment or build a piece of equipment for it. And in our lab, we actually will use a function generator. A function generator. And basically on the function generator, it will have is a output, coaxial cable out. And this will be a coax. And we'll have some buttons and we'll have some stuff. I'll be teaching you how to do that. And what we'll use on here is a square wave button over here. And then we'll mess with the frequencies and the voltages and stuff like that. But what I have to understand on this function generator is that it works only in a peak format. So remember, I said we work in 5 volts. Well, if you put in 5 volts thinking that's 5 volts peak, well, what you're actually going to be generating is almost 10 volts peak to peak, and you'll blow your circuit up. So just remember that when we put the numbers in, we have to remember that the unit's going to output peak to peak voltage. So keep that in mind. So it's going to ask you for a peak value, but it's going to output a peak to peak value here. The other way we could do to generate some digital signals. So again, we're looking at digital signals here. Is what we call a timer circuit. The most common is what we have called as a 555 timer. And this basically is really fascinating, and I'm going to have a different video on the 555 timer. But basically what it is a chip, integrated circuit, and that's what IC stands for, is integrated circuits. And on integrated circuits, basically you'll either have something with a little indentation right there, or you may have something that looks like this with a little dot. Well, when you have either a little dot here that's indented or this little hub right here, pin 1 is always to the left side of it. So this is facing up, the chip is facing up. Both are facing up, and you got these indentations to the left, and this is facing up. Pin 1 is right there, and this goes pin 1 to 4, then it drops over here 5 to 8. So if this was a 4, this was an 8-pin dip, dual line package. Dip is called a dual. That's called a dual line package. And basically what it means is that this is an integrated circuit. And integrated circuits are made of transistors and diodes and resistors. Basically, and some capacitors. Very simple circuitry inside, but very complex architecture. For this one's the same way. If you have this little indentation, the U indentations 1 through 4 again, and then 5 through 8. So where do you get all this information from if you need to? Well, it's called a data sheet. And data sheets will actually give you all the information you need in order to understand what this integrated circuit, what we call chip, does. So like I said, the digital signals are created by what we call timer circuits, and the basic kinds of 555 timer. The other one we have is called an oscillator and a crystal oscillator. Basically a crystal oscillator it uses a crystal. This is used as a crystal. And the crystals are usually set up in 1 megahertz ranges. usually about that range. But what's interesting, they have quartz. They use a quartz. They use a quartz. They cut quartz so fine, and then you would induce a voltage to there, a small voltage, and it causes it to resonate. When that resonate happens, it actually produces a frequency. It produces some sort of frequency that actually, if you put it into a special circuit and it actually reads it, you can come out with a digital signal. So basically, you can actually use a digital signal. So a crystal oscillator creates a digital signal, and so is the 555 timer. Both circuits are great. Both circuits, you can set them up to do what you want. You could set the pulse width of the 555 timer. You could set up the crystal oscillator to different crystal oscillators to generate different types of frequencies, and also pulse width. So there's a lot of applications to these things. So timers and crystal oscillators provide us a digital signal, and this digital signal is what we call a clock. Very important. It's called a clock. And we can actually, by putting special circuitry in here, and I'll talk about this in the next video, is that we could put in capacitors and resistors into the 555 timer or the crystal oscillator, and we could generate a digital signal. Interesting enough, the 555 timer, we can actually change the pulse width. So we could do a lot of different things with these digital timers. So you probably ask yourself, well, it's nice and dandy, but how do we actually check all this stuff? I'm a maintenance guy, or I'm an engineer, or whatever I am. I'm just out there, and I need to, see some of this stuff. And how do I actually visually see this? How can I test it? What kind of test equipment would I use? So the basic test equipment we use, would be your digital multimeter, and you set that for DC. And then you could get 0 to 5 volts. You could use that way. Some of the digital multimeters have very complex circuitry to them where you can actually get the frequency. We have a few of those in our lab where you can actually get the frequency. And you can actually measure different parts of the components too on it, such as capacitors and resistors. And you get those values to see if there's something that's wrong with that. The other piece of equipment is called a logic probe. A logic probe is basically a digital instrument that if it has a little point on it, and what it'll do is you hook it up to your 5 volts, and what you do is you touch it to one of these pins, and let's say you touch it to pin 8. We know that pin 8 is 5 volt signal. Well, if this chip is not working, the first thing I want to check to see if I got voltage at the 5 volts, and I also want to see what happens to my ground. So, excuse me, ground right here. This is reset. So I want to look at, I'll talk about the reset in a second, but this pin 8, if I don't have 5 volts, the chip's not turning on. If I don't have a ground, I got nothing. I can't control this. I can't control the chip. It's nothing's gonna happen. It's gonna be dead. So that's what the logic probe does. I take that. It's like my pen. I take it and move it there, and a little light goes on over here, and it says, "Oh, yeah, it's on. Good. Okay, we have that. Maybe it's our reset." A lot of times, what happens in this reset is that this reset is set to a high signal, but all of a sudden we have it shorted out to ground. Well, that resets the chip here. If that resets the chip, then this thing's not going to do anything. If it still doesn't work and everything's working, then we start looking at the different components that are going on. Maybe we even have a dead chip. So a logic probe could tell us a lot of different things. A voltmeter could actually tell us a lot of different things as well too. But a logic probe basically gives you all the information you need. If you really need to know what's going on in pin 3, let's say pin 3 is over here, and this is called the output, then we would have to use a different instrument. We can still use a logic probe to test to see if it goes high and low, because it's going to beep at you, it's going to light's going to flash. But if it's moving really fast, that logic probe is going to always be on. So what we use on this is actually an oscilloscope. And we have an oscilloscope and we'll be testing those signals. I'll show you how to use that. Now, you can also build yourself what we call a logic probe. And this is basically a resistor. We'll call this R1. And then we have a LED diode. And the symbol for LED diode looks like a regular diode. Has an anode and has a cathode that's positive and negative. And then it's touched the ground. So basically what we do, if we put 5 volts to this guy, so if we tap this guy, we tap this to our pin. So let's say this is our probe. And if we take this side and ground it, so we put it to ground, so you have your breadboard and you ground this side to ground, and you take this probe. Well, if this is 220 ohms, that's what we use, between 220, 330, and in some cases we even 100 ohms. Depends on what you do. probably 220 will be good, and often I'll explain to you why we use these numbers instead of something else. And there's other reasons we have to use like a 1K or 10K for this, but